Okay, here we go. So, starting now in chapter 2, there's a bunch of stuff to say about functions before we start talking about how to take derivatives of functions. So, this is actually going to take a while. It's at least a lecture, I think maybe most of 2 lectures. Anyway, it's going to be quite a bit of discussion. Just a lot to talk about. So, first of all, I do want to make sure that everybody knows what a function is. I know you've heard the term many times, right? The problem is that the way a lot of high schools treat this is a little bit fast and loose, a little bit sloppy, and it's important that we clean all that up so that we can do a careful treatment. It just when you get into multivariable calculus, there's more different things that can happen and more ways to misunderstand things, and if we're not precise, we're just going to get into big trouble. So the first thing to realize about a function, it's a trio. It's not just a formula. It's 3 things together. One of which is the formula. So what we're going to refer to here is the rule of assignment. Given an input exactly, how do you compute or determine the output? So again, very often this is a formula. But note in particular also, a function, part of the definition of a function is what the domain is. Where are you getting your inputs from that you're going to be plugging into this function? Right? And then, secondly, what I like to call the target, sometimes called the codomain. That seems a little stuffy to me. Target seems like a reasonable term. That's where the outputs go into. Right? This trio of things is what defines a function. Okay, now just as a silly example, let me point out, well, I guess I'll go ahead and do this first example first. Here's a function. We have a domain. All of the positive real numbers are allowed to go into this function called natural log. Right? There is a target. All of the values that you get when you compute natural log of a positive real number will always be real numbers. And then there's the rule of assignment, and the rule of assignment, I'm going to say it's just log. The actual, the details of the definition of natural log is not really what I want to focus on here. But computing the natural log is how you take a number from the domain and produce the corresponding output value in the target. Okay, is everybody with me so far? Note in particular this notation here, where we have function name, colon, and then set, arrow, set. Right? This is very, very standard. It's also very useful. It's very convenient. I'm going to be using it all the time, just nonstop to describe a function. I get a lot of information communicated very efficiently. So anyway, heads up for that. We're going to be using that as a shorthand for describing the name of the function, the domain, and the target. Okay. All right, so here's another bunch of functions. All of these functions here that we're going to talk about, the rule of assignment is, what is the student's ID number? It's not a formula, right? And it's also, why are we talking about that? We're not going to take the derivative of this function, right? It seems like a silly thing to talk about. But I want to point out, it doesn't have to be a formula. Right? It might be, and it usually will be, certainly in this class. It doesn't have to be. So, for any student, right, there is a corresponding ID number, which will always be an integer. Okay. Now, why is it that we have 3 differently named functions here if they're all the same formula, you want to say, namely rule of assignment, namely, look, just give me the student's ID number. Why do we have to give them 3 separate names? Well, you'll notice here, these 2 functions, f and g, have different targets. And that's fine. You don't have to, as long as all the outputs land in your target. Cool. Right? So, yes, every student ID number is an integer, sure. But it is also fair to say that every student ID number is a real number. You might say that's unnecessarily large to be the target. There is no such rule. It can be as large as you want it to be. It just has to be large enough that, all the outputs have to land in it. That's the only rule. So why do we care about the distinction between these two functions? They're defined on all students. They just have different targets, which is a kind of an arbitrary choice, seemingly. So who cares? It's going to matter at the bottom of this page of notes. And so for dramatic purposes, I'm going to wait on revealing that reason. But it really is going to matter. Okay. All right, what about this function and this function? Again, same formula, and this time, notice, same target even. The difference here is that the first function is defined for all students, and this second one is not. This second was defined only for students in this course. Again, it seems fussy and silly, right? But it's going to matter. We need to distinguish these as different functions, again, for reasons that will become clear at the bottom of this page. Okay. Alrighty. Okay, a little bit of lingo. I actually don't care for this term anymore, but what the book and many books define as, I'm going to go ahead and leave it in red because I don't like it. The range of a function is the set of actual outputs, not allowable outputs hypothetically, namely the target, right? The target is the set of things that are allowed to come out of the function. The range, as the book is defining it, is the set of actual outputs, right? So, for example, let's think about student ID numbers. We're allowing the student ID numbers here to be any integer. But there's plenty of integers that are not the student ID number for any student, right? For example, negative ones, right? No negative number, I would think, is a student ID number. Wouldn't that be weird? No 476-digit numbers are student ID numbers. Okay. All right. So do not conflate the target and the range. They are importantly different sets. Okay. Now, sadly, this term range is very commonly conflated with target. Depending on which book you pick up, they'll kind of interchangeably use the two words to mean the same thing, and they never really quite get around to being precise about what they actually mean as the definitions of these two things. And that's really unfortunate. It does cause problems, not in their books apparently, but in other contexts it does cause problems. The good news is this word, to my knowledge, is not. There is no sort of track record in the literature of it being conflated with target. So this is the term that I prefer for that reason. In fact, I am going to go ahead and scratch out over here where I wrote range and rewrite as image because I like that word better. It's less possibility for a misunderstanding with someone who learned out of a different textbook. Okay. All right. I guess I'll leave that there. Okay, so looking at this function here, we've got a function. Notice, name, domain, target. Here's the rule of assignment. This is how you compute the output values for any given input values. Notice that any real number can go in. You give me any real number, I can square it. Right? And notice that every output will indeed land in the target, namely will indeed be a real number. Okay, so there's my function I want to talk about. And with that noted, let's talk now about what the image is. What are the actual outputs sitting inside of here? What are the actual real numbers that are squares of other real numbers? Well, just the non-negative ones. Right? -3 is not the square of any real number. Okay. All right. So, as previously noted, notice that the image and the target are not the same thing. All right. Moving along. More terminology. When you have an equation expressing an input and an output from a function, the output, as previously noted, is called the input. Let me circle this differently. This is referred to as the image. It's the output. So now this is same word, slightly different usage as above. Above, when we talk about the image of a function, we're talking about the set of all outputs. When we talk about the image of a point, the image of an input value, here the input is x, the image of an input value is just that one output from the function. Same word, different context. So context will always make it clear which one is being referred to. So the output is called the image, and then analogously, the corresponding input that gave that output is called the pre-image, which I think kind of makes sense if you think about it. It came before. It's the thing that led to the image, if you will. All right, so image and pre-image, very useful terminology. Specifically, we're going to use the term pre-image down here when we define. I guess I better leave. Yeah, okay. Better leave it like this. We're going to use the notion of a pre-image to define what we mean by surjectivity, injectivity, and bijectivity, which are, mouthfuls. Very complicated sounding words if you want to intimidate your friends. It's good for that reason. Casual parlance, surjective is very often referred to as onto. Injective is referred to as one-to-one. Okay, so what do these words mean? It refers to looking into the target and seeing how many pre-images there are for every point in the target. So let me just show you some quick examples before I get to those definitions. Well, let me not do that. This point here, by the way, the way I have this picture drawn, that's the domain. That's the target. We're looking at points in the target, and then we're going to work backwards and ask how many pre-images does it have in the domain. So this point right here has, you'll notice, 2 pre-images. There are 2 points in the domain for which the output gives you that output value. Everybody cool? Okay, so this point has 2 pre-images. Notice this point here has 0 pre-images. It is not the output for any input for this function. Okay, so now let's talk about injectivity and surjectivity. Let's see here. Let me make color choices. Surjective, aka onto, means every point has at least 1 pre-image. At least 1. So now looking at these, symbolic functions that I have down here, notice that one is surjective and that one is surjective. Every point in the for each of these 2 functions that I've got checked, every point in the output is an image. Every point in the output has at least 1 pre-image. Okay. Now, injective, aka one-to-one. I need to know that every point in the target has at most 1 pre-image. No more than 1. So, okay, well, let's see here. That one and that one. Okay, so why do we care about these terms? Well, they come up in various different places, but what we're going to mostly do with them is we're going to talk about what it means when a function is both. Namely, every point in the target has at least 1 and at most 1, namely exactly 1 pre-image. And if every point has exactly 1 pre-image, notice this is the only one here. Both injective and surjective. It's got both of the jectives. It's bijective, right? That's the term, bijective. this would be an example of such a function. And the reason we care about these functions is that when you have both of these properties, the function is invertible. And that's an important algebraic feature that we need to be able to use when it's a thing, and that we need to make sure not to use when it's not a thing. Right? So let me try to explain why such a function is invertible. Of course, you all know what an inverse function is. The inverse function says, all right, instead of going to the right, the idea of an inverse function is I want to take output values and ask, okay, well, how do I go backwards? I want to define a function that carries me the other way, and for every formerly output value, I want to determine a formerly input value as the inverse function of that output, right? Presumably you all have seen this idea before. And notice, you need to know that there is exactly one preimage in order to do this. You can't define the preimage, I emphasize, preimage of this point, because I got two choices. Which one of these do I pick? If I'm going to say I have an inverse function, I need to know, there cannot be any ambiguity in the definition of a function, right? So here I've got too many choices. I don't know what to do. I can't define f inverse of this point. Okay, too many options. And likewise, I need to make sure I have enough options, right? I can't define f inverse of this point here either. There's nothing to go back to. Right? So you have to have both. You have to have exactly one preimage to be able to do this move here. Like that. All right, now let's see some algebraic examples of this. This function right here. Notice the domain, the target, the rule of assignment, aka the formula. It's not invertible. Right? If I were to say let me ask you this. What is f inverse of 25? What input value, singular, what single input value when you square it gives you 25? But there's two of them. There's 5 and there's -5. They're both perfectly allowable. They're both in the domain. I can't just arbitrarily pick one. So, not invertible. Also, what would be f inverse of -25? Got nothing. Right? So this function's got all sorts of problems. It's not invertible, very importantly. Now, this function here, which you'll notice looks a lot alike, and in a high school context, you'd be tempted to say, come on, that's the same function, it's x squared, come on. Right? Let's not be all uptight about this. But this function here is invertible. Right? Because the inverse only has to be defined for non-negative numbers. And all non-negative numbers do have at least one square root. So this can be the domain of our inverse function. And then likewise, notice that my original domain here is only the non-negative inputs. And for every real number that has a square root, it has exactly one non-negative square root. So that can be our target. And this function I have highlighted in purple is invertible. It's 1-to-1 and onto, bijective in other words. And so I can define its inverse. And here it is. There's the inverse function. Okay. Is everybody good? Yep.
So the domain and target of the inverse function is always the reverse of the original.
That's exactly right. Yep, exactly right. Here's another example. A lot of people like to talk about the inverse of sine theta, and I get the motivation to want to do that, right? It's a useful function, arcsine. Problem is you do have to, again, be careful in how you define the sine function in the first place. If you just say, sine is a function into which I can plug any real number and out will come, a real number, right? If you're too careless about it, not invertible. You can't invert the general, broadly defined sine function. But if you restrict your domain like this, so that your inputs are only those values there, right? And your allowed outputs are only these values there, right? This is a perfectly invertible function, no problem, right? That formula, that curve right there, in some sense, y'all know how graphs work. You give me any green number, there is exactly one corresponding blue number. And vice versa. Okay. All right. By the way, for whatever it's worth, I think this is an interesting observation. I will point out that you might say that this is the equation that describes this curve here that we're looking at. And as such, we're talking here about the graph of the sine function. So y is sine of theta, right? And that's fine. That's fine. But here's the thing. This equation here describes the exact same picture. You could make the case that this is a kind of really the graph of the arcsine function, because, well, for every output there is exactly one input, and you give me a y, there is exactly one corresponding theta. The only questionable thing as to whether this is actually a graph is, are you allowed to have the output variable be the horizontal axis? Are you allowed to do that? And yeah, sure, totally. I mean, we don't usually, but there's nothing really morally wrong about that, right? So I think it's a neat observation that if you want to invert a function for which you have an existing graph, you don't need to flip it over the 45-degree line. The only purpose that would serve is arbitrarily, obeying a pointless rule that the outputs have to be vertical, which isn't really a thing. Okay. All right. Terminology. Let me be quick with this. When you have a function like so, notice the domain is Rn, the target is Rm. By the way, notice further, if the domain is Rn, that means that what goes into this function is a point in Rn, aka a vector in Rn, right? The same thing, kind of. Aka a list of coordinates describing a vector in Rn. So you might say that what goes into this function is a list, an ordered list of n real numbers. So, anyway, that's one way to think about it. Likewise, what comes out of this function is an ordered list of m real numbers, otherwise known as a vector in Rm or a point in Rm. So take your pick. Either point of view is fine. Okay, so the terms real valued and vector valued refer to whether what comes out is either a single real number or a vector, namely a list of real numbers. And it all turns, of course, on whether or not this number here, m, is one or more than one. Right, so real valued, vector valued is just referring to, in some sense, what are the outputs for this function. Likewise, the terms single variable and multivariable, they refer to the inputs and whether you have a single input variable or whether you have multiple input variables, aka the input is a vector. All right, you might wonder, in fact, well, why don't we call it a vector variable function? We certainly could. Just doesn't seem to be in the common parlance. And of course, all this turns on whether that number, n, is one or more than one. Okay. All right, just a little bit of terminology. And then real quick, notice if the output vector is a function of the input variables, individually, one at a time, the output components are also functions of, well, all of the input variables. And so y1 itself is a real valued multivariable function. Right? So just to be clear, real valued because we're looking at just the one real output, and multivariable because we're looking at that as being a function of all of the inputs. Okay. All right. Okay, so vector valued multivariable functions, right? Sort of the worst case of the above. Multiple inputs, multiple outputs. A lot of people come into a class like this and think that, okay, well that's weirdo, obscure, come on, what does that got to do with the real world, right? And answer, it is all over the place in the real world. The weather, right? The most trite of water cooler conversations, right? Is in fact a discussion of a vector valued multivariable function, because if you're going to talk about the weather, there's a bunch of characteristics of the weather, right? Temperature, barometric pressure, wind speed, humidity. That's just off the top of my head. I'm not even a meteorologist, right? And there's a bunch of different aspects that describe what the weather is wherever you might happen to be. Right? And it depends on lots of things. It depends on where are you. Latitude and longitude. Where on planet Earth are you? The weather's very different in France than it is in Durham right now. Right? Depends on how high are you above sea level. Right? Now, not that you are very often above ground. Most people spend most of their time on the ground. But if you get up in a plane or a hot air balloon and you're 3,000 feet, but you're going to notice the weather's very different up there. Right? And of course, it depends on when you're talking about the weather. The weather in Durham is not a constant. It changes. Right? So there's multiple inputs, thus making this a multivariable function. There's multiple outputs, thus making this vector valued. And again, we're just talking about the weather. Everybody with me? All right. Okay, so, how do we draw these things? Now, I have to give you all a warning here before we go on. We're going to define first something called a graph. I know you all have heard of graphs, and I know for sure you've seen graphs, and you've probably used the term quite a bit. In single variable calculus, almost every picture that you draw is a graph. Certainly, almost every picture that you draw of a function is the graph of that function. It is so nearly universal that in a single variable calculus class, you can actually get away with actually conflating the word graph with the word picture, because pretty much all the pictures are graphs, so why be fussy, right? So here's the bad news, and this is important bad news. This will not continue in multivariable calculus. We're going to be drawing lots of pictures of functions that are not graphs. We will draw some graphs, but we will draw many other kinds of pictures, and we're going to go through and talk about a lot of them. Not all of them, but a lot of them over the next remainder of today's lecture. And we'll introduce a few more as time goes on. So, before we do any of this, I want to warn you, please be very, very careful with your terminology going forward. Again, you can kind of afford to be kind of sloppy. Again, let's see here. The words function and graph and picture are usually just kind of blended together and conflated in single variable calculus classes. Then you can kind of get away with that, and nothing really all that bad happens, and so who cares? All of those are going to be different things in this class. So what we're looking for here, the reason that I'm going to spend time in class talking about this stuff, is to focus on proper use of the terminology. The algebra that we're going to see over the next several pages is practically trivial. There's almost nothing that happens algebraically. There's almost no sort of like using trig functions or laws of exponentials. Nothing algebraically challenging, right? It's all proper and careful use of the terminology. Okay. All right, so let's talk about a graph. A graph is, here's my definition of it. This is unnecessary. This is more complicated than we're going to be working with most of the time. But notice the graph is a set. It's the set of points that satisfy certain conditions. By the way, this is called set builder notation. I hope y'all might have seen this before. If you want to describe a set, a very common and convenient way to do this is use curly brackets. To the left of the vertical bar, you indicate what the objects in the set look like. And to the right of the vertical bar, you put your constraints of, what requirements must those things satisfy. Okay, so when you're talking about a graph, the graph is a set of points where the first several coordinates come out of the domain, right? And the second several coordinates are the corresponding output values that come out of the function, and thus those output values in some sense are in the target. Okay, so another way to say it is you take the input point and the output point and you kind of smash them together to form a big sort of uber point that has both input coordinates and output coordinates all in the same point. Okay, so let's see an example. Again, I know you've seen this before. Here's a single variable example, and we're going to look at a real simple function, y equals f of x. Notice that a point on the graph is an ordered pair. The first number in that ordered pair is the input value, which we're going to represent here as the horizontal coordinate. The second coordinate in that ordered pair is the corresponding output value. That didn't work right. There we go. The output value we typically represent as the vertical coordinate. Right? Yes?
Why do you have to specify D to be a subset of the domain?
I'm just making my definition just more general. I don't want to feel obligated to only be able to talk about graphs of functions that are defined everywhere, right? I might have a function like take a natural log, right? I can't define natural log on the whole real number line, and I don't want to have to. I want to be able to talk about the graph of natural log, and so by allowing myself to have a domain that's merely a subset of a Euclidean space, that opens up my options more, and I can talk about more graphs of more functions. Does that make sense?
So D is kind of the actual.
It is nothing actual about it. It is the domain. Full stop. Yeah. Now, so the domain is D, right? And then side note for user convenience, I'm going to note that my domain is a subset of Rn. But all this business here about subset, I can erase this and nothing bad happens particularly. Domain is D, target is Rm. Yeah. And I put this information in here because it is kind of convenient to be able to see, okay, well, yeah, all of those points in the domain are going to have in coordinates. And that's just kind of useful information. Yeah. Okay, so point on the graph. Again, green is the input coordinate, blue is the output coordinate. You see that algebraically here, you see that geometrically over here. The ordered pair, then, is a point on the graph, and the entire graph is what you get when you look at all such points. So, hopefully familiar. We're being a little bit more precise about this than perhaps you were in high school calculus and algebra classes, but that's going to be important going forward. Here's the next up. Here's going to be our first multivariable graph. Let's talk now about a function from R2 to R1. All right. So now, typically, if we're gonna give the output values a name, just for a sort of alphabetic convenience, I'm going to call it Z. So X and Y are the inputs. Z is the output. Again, no law about alphabetical order or anything like that. This is just kind of arbitrary and standard, convenient, I'll say. So, okay, what are the inputs to the function? The inputs are, well, x and y. It's arguably, again, so this function is defined by an x-coordinate and a y-coordinate, namely by a point in the xy plane. That's the input. 2 coordinates. Okay, the output, third coordinate then, the output, calling z, is, well, it's the height here, if you will. Saying how far to go up, like so. So again, the way I've chosen to lay things out, the inputs are both horizontal. I've got 2 horizontals, right? But my inputs are horizontal, my output is vertical. Not that you have to, but just for convenience, here I am. And the points that you get as a result, like this point right here, are points that are on the graph. And the actual entire graph is the collection of all such points. So looking at the picture, it's like we're going to take every point in the xy plane and we're going to push up by whatever amount the formula tells us to push up. And the result is going to be that that's going to create a surface. So the graph of a function from R2 to R1 is a surface in space. Everybody okay? All right, now real quick, I want to point out a different way of thinking about this. You know, very often we won't actually be writing down sort of, all of this. So in practice, how do you identify, an equation, for example, as representing a graph? And really, if you think about it, all you need is that one of the variables is what you might call solved for. One of the variables is given explicitly as a function of the other variables. Because whenever that happens, then you can say, all right, well then those are the inputs and these are the outputs, and you can assemble your x, y, z's accordingly. And so, algebraically, the giveaway is actually pretty simple. One of the variables is solved for. That makes it a graph. So, easier to kind of notice it that way. Okay. All right, so now, how would I form a graph of this function here? A mere 3 inputs, right? That doesn't seem that scary. 3 is it's one of the smallest numbers that's bigger than 1, right? It doesn't seem like it should be that bad of a story. But notice, if you're going to talk about a graph of this function, well, there are 3 inputs and then 1 output, and the graph is going to involve taking the 3 inputs and the 1 output and assembling a bunch of points that have all of those variables, inputs and outputs, all of them as its coordinates. And notice this would be a picture in 4 dimensions because there's 4 coordinates there, and we can't even pretend to do that. This is out of the question. Right? So we cannot draw the graph of this function. Yep.
Why is this function producing an output in R4?
Nope. So the output of this function, the output is a real number. That real number is called W. Right? So the point on the graph, you have to keep in mind, points on the graph are not just outputs. Points on the graph are points whose coordinates are both inputs and outputs. So I've got in here all 3 of the inputs and the single output, making for a total of 4 coordinates for the point on the graph. But the graph is not the same as the output. That make sense? Let's go back up to the single variable example, right? Nobody's creeped out by this, but there's only 1 output, and yet the picture is 2-dimensional.
Okay.
See what I'm saying? Yeah. Right? And so the reason it's 2-dimensional is because, well, that point is, well, it involves both the output and the input together. Yeah. Right. So one way you might say this is graphs are dimensionally wasteful. you need a lot of dimensions to draw a graph. If you think about it, in some sense, single variable functions, real valued single variable functions, are kind of the best. I mean, you can't really go any higher than that without getting into dimension trouble, right? Here we have a single variable function. We have a two-dimensional picture that's already as big as our two-dimensional paper can handle. We kind of had to fake it. Even with the function of merely two variables, I had to, optical illusion. Look, the x-axis is coming out of the screen at you, right? No, it's not. It's a two-dimensional picture. So I'm pretending to draw the graph here. Didn't really draw the graph. Everybody see what I mean? So graphs are problematic in that sense, right? You're going to run out of dimensions fast. That's one of the reasons why we don't just exclusively use graphs in multivariable. We kind of can't. Okay. All right. So I've already given y'all this speech, but let me just remind you, we really have to be careful with, conflating a graph of a function, which is a picture, with the function itself, which is an algebraic object. Definitely different things. And furthermore, there is going to be other ways to draw pictures of functions that are not graphs, that are importantly not graphs. And so again, if you're kind of using the term graph fast and loose to refer to any picture that in whatever sense relates to a function, you're going to get in trouble with your results. Okay, next one. This is what I like to call the literal picture. Don't forget what a function does. A function has a domain. So let's draw the domain. The function has a target. Let's draw the target. Don't forget what the function does. The function takes point out of the domain and puts them down into the target. So I'm going to visualize, by way of this picture here, that all the points in the blue space are going to be thought of as being thrown over and landing in the green space. And just as for example, I'm going to think of this point here, A, as going into the function, and when it comes out, it lands on this point here, F of A. So you might even, if you want to, draw an arrow like that says, okay, that input point goes to that output point. And I like the term literal picture because this is, about as literally describing what the function does as you can get. There's really kind of no arbitrary choices here, but there's a domain. There it is. The function's got a target. There it is. And I'm trying to just represent as basically as possible what the function does from one to the other. So now this does not look like a useful picture, right? After all, what I have drawn on the screen here only represents what's happening to just the one input value. Right? Now by comparison, let's come over to here and look at, good old single variable calculus days. In single variable calculus days, we were drawing pictures like this, and we didn't just draw one point at a time. We draw the entire curve. That curve helps me understand what's happening to every input value to the function, and I can see all of the output values. So how sad that here we can only see what's happening to just the one point, right? So yeah, I'm going to acknowledge that's disappointing. But notice further, though, graph is not on the table. All right, so how this picture of a function of three variables compares to this picture of a function of one variable is an unfair comparison. What we should really do is compare this picture of a function with three variables with this picture of a function of three variables. Oh, that's right, we can't draw that picture. All right, so in a fair comparison, the graph is a 100% loser in this case. And this literal picture is, it kind of wins by default, right? But still not particularly inspiring. But actually pretty natural. Now, I'm going to show you one other thing about this picture where this does get really useful. Very often what we're going to be doing as soon as tomorrow is looking at particular points in the domain, thinking about what their image is, and then asking, okay, what happens if this point in the domain were to start moving with some velocity? And if you think about it, if the input point starts to move, then that output is also going to be moving with some velocity. And so I would like to come up with various different ways of thinking about how I can relate, in some sense, let's be vague about it, but how can I relate this, what you might call input velocity, with this corresponding output velocity? Like a reasonable question, perhaps, I hope. And notice how this picture is actually really useful for that. I can see the input velocity, I can see the output velocity, and that kind of represents what's going on. Yes, to be fair, still only at the one point, right? But still, I do have a geometric sort of context in which to think about what's going to be happening algebraically. Okay. Alrighty. Okay, here's another kind of a picture. It's called a level set. You may have seen level sets before. You may have heard the term before. Again, I'm going to write down the full definition, and then I'm going to show you some, day in and day out, realistically working examples. But the simple idea is that a level set's a pre-image. We've already talked about pre-images. I'm going to write that out a little bit more fully here. There's our definition. So given a multivariable function, a level set is this set here. So again, given a certain, I wanted that in blue, sorry. Given this output value sitting inside of Rm, given an output, the level set is the set of all input values, right? It's the input values that, when you plug them into the function, give you the designated output value. This is pre-image. Right? Okay. Notice, now this is just kind of for intuitive purposes, doesn't really matter, but we're starting with an output value here, and what we produce is a subset of the domain. So given a blue output value, this construction produces a green pre-image in the domain. And notice the arrow kind of goes backwards, right? Given an output, we're going to determine a bunch of inputs. And because the arrow kind of goes backwards, that's why we use this notation right here, F inverse of B. Now this is an abuse. There is no inverse function, presumably, probably. Certainly we're not going to assume there's an inverse function. So F inverse is a sloppy abuse notation, but it's kind of an accepted, understood sloppiness. It's convention, and everybody knows what it means. Everybody knows that it's not actually that F is invertible, and it's okay. Nothing to worry about there. So yeah, given a blue output, going backwards, looking at the corresponding inputs, we refer to that as F inverse. Even though it's not actually invertible. Okay. All right. Now, most of the time, we're just looking at real valued functions. I wanted to define it in general just because we can, but in practice, I can't even think off the top of my head of any examples we're going to do in this class that are not real valued. Yep.
So does the function has to be bijective?
Nope, it's not. No, that's the whole point. Yeah, this function does not have to be invertible, and you're right that this seems to be suggesting there's an inverse function, right? But there isn't. And that's why this is an abusive notation. And so again, confess. Yes, I confess this is an abusive notation, but we're going to use it anyway because it's pretty standard, and it conjures again the idea that we're kind of going backwards through the function to get our preimage. Yeah. Okay, so here's a couple of in practice, easy examples. So here I have a function, 2 inputs, 1 output. There's my formula. 2 inputs, 1 output. And let's look at the output value 1. All right, and let's ask what is the level set corresponding to the output value 1? What is the pre-image of 1? What is the collection of all inputs in the domain, which when you plug them into this function gives you 1? Well, I need for x squared plus y squared to be 1. And that's this circle here. Everybody cool? So likewise, let's see here. Let me do it like that. Let's now think about, this output value 2. Well, 2, what is its level set? Well, we're going to be looking at where the value of f is equal to 2. And that's x squared plus y squared equals 2, which is a slightly larger circle. So notice that my level sets of this function are curves in the domain. Everybody happy? Yep.
How would you graph, for example, f inverse of -1?
Okay, so I have to take two exceptions to what you do. You said the word graph, right? Now, I know, I get it. You've got 20 years of history of using that word, and getting away with improper usage. So I didn't mean to pick on you. So let's be careful, right? We don't say graph unless you mean specifically the graph construction. And now let's see. You want me to draw the level set f inverse of what?
-1.
There is no such set, right? Because the preimage of -1, you ask what inputs give you -1, the answer is no such inputs. So I guess you could say that level set is the empty set. Yeah, there's just nothing there. Okay. All right, now here's a real-world example where you possibly might have seen level sets before. That's contour lines on an altitude map or a topographical map, they call them sometimes. So if you think about it, you can talk about the altitude function, which, depending on where you are, any point on the map, right? You can ask what the corresponding altitude is at that point. Right? So, given a point on the map, what is the corresponding altitude? Well, if you set that altitude function equal to a constant, and by the way, that's another sort of algebraic giveaway. Notice, all of these level sets over here, I'm taking the function and I'm setting it equal to constants. That's sort of the tip-off, again, that you're looking at a level set. If you set the altitude equal to a constant, you're going to get various different curves that look, kind of like this sort of thing here. And by the way, let me label these a little bit more carefully. Let's see here. Let me go into pencil mode. This curve here, that might be where altitude is equal to 100 feet, let's say. And then this curve here is maybe the set of all points where the altitude is equal to 200, etc. Right? So you do that for all the different altitudes in the vicinity you're talking about, and you can produce a picture kind of like that. And this can be helpful in deciding where to, how am I going to get to the top of this mountain, for example. And as a for example, if I needed to get from, let's say, this point up to the top of the mountain, namely that point, I am not doing this. I think that's a bad idea. I don't know, maybe that's my age talking, right? But I don't want, that looks really steep, especially near the end. Check it out. Over here near the end, I'm going to be gaining 100 feet of altitude over a very short horizontal distance there. That looks really steep. I don't want to do that anymore, right? So what I would probably do, and I'm going to credit the map in making this easily determinable, I would probably do something, I would try not to hit my elbow on the thing. Sorry about that. But I would probably do something kind of like this. Now that's a longer path, but notice every 100 feet that I gain is gained over somewhat of a distance. This would be the most worrisome part for me, where I gain 100 feet over not that much a distance, right? But nowhere near as bad as this nightmare right there, where I gain 100 feet of altitude over hardly any horizontal. That's bonkers steep. So this purple path there, much more reasonable. Now, just for fun, I happen to have here a what is this? The Parks Department or something put out this topographical map. This is a mountain that in my youth I actually climbed. I'm not recommending it. It was a lot of work. Oh my gosh. So if you want to get up to the top here, right? What's the best approach? What you're absolutely not even going to consider doing is this. That is insane. That's so steep you wouldn't even believe it. In fact, I can just tell you again, personal experience, when you're at the top and you're kind of looking down that way, you're not looking down like that. It's about like that, right? It's just insanely steep and horrifying. So that's out of the question. And you can see even kind of up this side, maybe not as bad, but more reasonable. So the approach that you take to get up to the top is you come up like this. And it's kind of a ridge line there. But you go up that way, and it's still pretty steep. It's hard going. And by the way, you can't breathe because you're at, what's that, 13,000 feet, right? That oxygen's very thin up there. So that is a tremendous exertion there. But that's the best available option. And you can see it, again, because of the contour lines. Let me also point out, you can see a little lower down here, here it is, what they call switchbacks. Right? All of this right here. The purpose of switchbacks is so that you don't have to go straight up the steep hill. So you get, instead of, for example, instead of going from here to there over a very short distance, right? You get to do that altitude gain over a longer horizontal distance, and therefore it's not as steep. So again, the goal is to try not to cross these contour lines too quickly. And the switchback, the zigzaggy switchback thing, is a way of helping you avoid cutting those lines too quickly. Okay. All right. Okay. Now, we've talked about graphs. We've talked about level sets. They're absolutely different things. Quick reminder, again, we've already discussed this, but the graph is what you get when you set the function equal to another variable. Level set is what you get when you set the function equal to a constant. Right, so algebraically, they're completely different constructions. But what you notice is that if you've got the graph already made, and then if you say, okay, I'm going to take a horizontal cross-section of that graph, if you think about it, z equals a constant means you're going to set height, z, equal to a constant. That means you're taking a slice horizontally, otherwise known as a cross-section. Altogether, a horizontal cross-section of the graph of the function effectively sets f equal to c, namely level set. So we get this really nice conclusion here. Let me clean this up. Really nice conclusion is that level sets are horizontal cross sections of graphs. Now let's see this in action. Here's an algebraic example. Let's see here. I get my colors. Okay, so green for graphs. Okay, that's easy to remember. Okay, so looking at this function f here, there's what the level sets look like. If I can draw. Level sets are various curves. Okay, what does the graph look like? The graph, again, notice same function, but I'm setting equal to z, a new variable, instead of c, a constant. The graph is, and I'm going to justify this later, but for the moment, let me just assert that this is a kind of a bowl-like shape that looks like that. It's called a paraboloid. We'll justify this picture a little bit later, hopefully today. Fingers crossed. So, first thing to note is, again, very different. These are not the same picture. Can you imagine how wrong it would be to refer to this as being a graph of f? It's really, really not. It's not just that it's slightly wrong. No, it's wildly wrong, right? So be very careful with the terminology. Again, you go around saying graph when you don't mean graph, and you're going to be, guilty of this level of nonsense. Right? Okay, but now let's talk about taking cross sections of the graph per the observation that we just made. You take those cross sections of the graph, and notice what you get are, in fact, these circles. So again, horizontal cross sections of graphs give you level sets. There's one little minor, annoying little distinction that I do have to point out here, and apologies for the technically, what I have here are circles in 2 dimensions, right? Points on those circles only have 2 coordinates. All right, well, these circles here are in 3 dimensions. They have 3 coordinates. So when I say that they're the same, what I mean is, okay, well, yeah, but once you've got this, look at their projection down into the XY plane. In other words, throw away the Z's, and when you do that, you will get literally and exactly those circles. So, minor formality there. Okay, now, we've talked about given a function, you can make the graph, you can make level sets, etc. I want to go backwards now. Given a set, what are the functions that you can use to describe it? Not given a function, what are the pictures that you can generate, but given a picture, what are the functions that correspond to it? So, all right, so just to kind of get the ball rolling here, let's imagine that we're looking at this line here that I've got a picture of like so. That's a line. What function does that represent? Okay, there's actually a bunch of them, and the question is vague, right? So again, you cannot conflate a picture with a function. What function in what sense might be a reasonable retort? Right? You don't ask me that's not a function, it's a line. You want this to be the graph of a function? You want it to be a level set of a function? In what relationship are we talking about here? Right? So that's the thing. There are multiple different functions. This picture is the graph of that function. It's a level set of that function. and it is parameterized by that function. Notice these are three different functions that in their own different ways, depending on what construction you're talking about, the graph construction, the level set construction, depending on what you're talking about, can represent this line. Right? And this is one of the places where students very often step on the landmine. So let me kind of reveal something that's going to happen when we get further into the course. We're going to start doing some calculus somewhere along in here, right? Next couple of days, maybe. I forget exactly. Anyway, which one of these functions should we do calculus to? Should I be doing the calculus of this function? Should I do the calculus of this function, et cetera, et cetera? What we're going to find is that for these different geometric constructions, calculus just looks different. So I'm going to talk, for example, about the calculus of graphs. And when we're talking about the calculus of graphs, we're going to be doing certain kinds of derivatives, and we're going to make certain kinds of geometric interpretations. Those geometric interpretations will make sense only on the graph, because we're doing the calculus of graphs. So depending on what you want to know about this line, maybe you need the calculus of graphs, in which case this is the function you should be looking at, and not these. On the other hand, you might want to know something totally different about this line. Maybe you want to know something that is part of the calculus of level sets. And again, there's going to be some neat facts that we're going to find. And when you're doing calculus, if you're looking at a picture of level sets, there's certain kinds of geometric interpretations that we're going to get. And if that's what you want, if that's the what you want to know about this line, well, you'd better be looking at and doing the calculus of this function if you're going to make an interpretation of the calculus of level sets. And not that one, and not that one. Everybody see what I mean? So it's critical that we distinguish between the calculus of level sets, the calculus of graphs, and the calculus of parameterizations. They are all geometrically different. Okay. By the way, this is a nice exercise here to persuade yourself of, and I'm going to leave most of the details of this to y'all. I'm going to leave this one to y'all and this one to y'all. Those are easy checks, but do make sure that you're solidly comfortable with my claims in 2 and 3. I do want to persuade you, though, how I got this function, where I dreamed that up. Looks like I pulled it out of thin air. First, let me persuade you that what we're looking at actually is the graph. Keep in mind, if I want to take the graph of this function, I set the function equal to a new variable. This is what it means to take the graph of that function. And then you can do a little bit of easy algebra for yourself and persuade yourself that these two equations are actually equivalent. Right? I mean, you were just throwing terms around. Algebra 1, easy algebra 1, in fact, right? So given the function, taking the graph, we reproduce that equation. But how did I go the other way? I went the other way by noticing what happened in going the other way, which was, which was that effectively I solved for the variable y. Right? So when you have an equation in which you can solve for one of the variables, when you do so, you're rewriting that equation as being the graph of whatever function you get when you solve for it. Okay. All right. Okay. All right. And I've already talked about all of this down here. I've already talked about all that. Okay. Let's see here. Neat fact. Useful fact. It turns out every graph is a level set. Unexpected. Now, I emphasize graphs and level sets are not the same thing. I do hear that it sounds like I contradicted myself, right? Very importantly, every graph is a level set of a different function. Certainly not the same function. Never the same function. But nevertheless, if you have something that's given to you as a graph, you can rewrite it as a level set. It's just going to be a level set of something else. So here you go. It's easy observation. I claim that this is the graph. You can see graph right there because one of the variables is solved for. It's the graph of this function, which you see has n inputs and 1 output. So this is our starting point, starting with a graph. I claim that this graph is a level set. Now let me be careful about this. What do I mean by is? I mean this algebra is equivalent to a level set. Now reminder, what is a level set? A level set is what you get when you set something equal to a constant. Now I do indeed have on the right hand side over here a constant. This bottom equation, something is being set equal to a constant. That thing, this is the function whose level set we're looking at. Okay, so here you go. Everything in the given here. Let me color code a little bit better. We started with a graph. We ended up with a level set. And again, the key is that the function whose graph we're looking at, the function whose level set we're looking at, that's the same thing. Those functions are different functions. Everybody with me? So, for example, suppose, and I have an algebraic example to follow here. Suppose somebody gives you a surface that is a graph, and they ask you a question about that surface, and you think to yourself, oh man, but it's a graph. The calculus of graphs doesn't give me what I need. Wouldn't it be nice, wishful thinking, but wouldn't it be nice if this was a level set, because the calculus of level sets would tell me what I want or get me something closer to what I want. Golly, I wish I could apply the calculus of level sets, but I can't. I can't apply the calculus of level sets because I'm looking at a graph. What you do in that circumstance is say, okay, well, it's written as a graph, but I'm just going to rewrite it like so. Now it's a level set. Said differently, all I need to do is apply the calculus of level sets to this function down here. Not that function, right? But apply the calculus of level sets to this function here. And you win. So it's nice to be able to convert back and forth like that. So just to get some algebra on the page, let's suppose that you're looking at the graph of this function here. So here it is, the graph. I should be careful with my colors. The graph, so z equals, of this function. World's easiest algebra, just kind of toss some terms around. Nothing hardly happened there. Nothing mysterious happened there. But notice that as a result, I am now looking at a level set of my new function right there. And we're going to very soon, soonish, we're going to be learning some calculus of level sets. And so this is the function to which I will apply the calculus of level sets to draw some neat conclusions that are very hard otherwise to do from a graph point of view. Okay. All right, a little bit of bad news. Oh, how am I on time? Okay, this will be a good ending point. Not every level set is a graph. Every graph's a level set. Different function and all that, of course. But you just cannot turn it around the other way. Easy example. Here's a level set. Right, that's a level set. It's a level set of this function right there. And I can see right away this just absolutely is not a graph because it fails the vertical line test. Right? So this is not y equals anything. There is no function for which y equals that function would give you this picture. So, too bad. Okay, we're out of time, so we will draw it right there, and see y'all later. Have a good one. We did not finish section 2.1 here, I guess. So I'm going to have to break up the assignment into parts like I've done before, and so that's going to take me a little while to get the homework assignment done. Certainly before I leave today, I'll have today's homework assignment posted. Okay, see y'all later. Have a good one.